So let's start with today's lecture. I haven't been talking about the logistics. Sorry that I faced a number of deadlines myself in the past 2 weeks. So there have been quite a lot of backlogs. Also, we are sort of moving towards the end of semester, so we sort of I guess it's just naturally that we sort of need to intensify the study a little bit. But in general, just don't worry too much about that. I have been reading your homework assignments and midterms. Most of you have been doing fine. And also, as what we move towards the end of the semester, we are going to add a lot more extra office hours and tutorials. So in my experience, that you guys usually just also try do a little bit of speed up like towards the end of semester. So this model have been working pretty well. So we just study a lot more in the next few weeks, right? So in terms of the timeline, this is my goal. So I owe you both assignment 2, programming assignment 2, and midterms. And assignment 0 is actually bonus. So that's the reason I didn't feel that it was urgent to return things to you. But in any case, I'm going to try to return all of this to you like within this week. I noticed that I promised to return you like by the end of the last week. I missed the deliverables. So sorry, really sorry about that. I will try to speed up. So the next thing would be the mandatory meeting. I'm also going to set up the schedule like we did for the first time to set up our second mandatory meeting. Some of you already met with me, so basically, in case you already met with me for the second time, you can just you don't need to sign up for the second mandatory meeting. And also, starting from the next week, I'm going to add one extra office hour and slash tutorials. Tentatively, I'm going to put my third office hour in on Saturday morning, 9 a.m. to 12 p.m. So, I guess it's really just that as we are all moving towards to the final, so that I sort of want to make sure that we do there are enough resources available for each of you to really get through this course. Okay, so in case you have any questions, just email me. So today we are going to talk about the network flow. I remember last lecture I sort of make a mistake. I thought we had one more lecture on dynamic programming, and actually, the shortest path algorithm with the negative weights was actually the hardest dynamic programming we were facing. So today we are going to move to a new topic, that's the network flow. One interesting thing about this kind of network flow is probably this is the first time you saw some of the mathematical results that are more or less getting close to the Nobel Prize quality, right? The max flow mean cut problem sort of belongs to the general class of the prime module problem, right? So, it's also closely related to some linear programs to linear programming. In case you have done learned this topic in operations research. So in general, in the I think at least in the 50s, in the 20th century, like people have been working on this topic quite a lot, and I think some of the scientists that actually won the Nobel Prize in economics because of this kind of understanding this kind of primordial structures, right? So at least personally, I felt quite excited when I was undergrad student when I start to really eventually being able to sort of move towards like the very complicated mathematical topics like after years of studies in computer science and mathematics. But it's not that complicated as you really see like when we put this problem into the graph algorithm context, like everything is really just unfolded quite naturally. So on the other hand, don't worry too much about that. So, so now we start with trying to formulate the flow problem, right? The flow network. The flow network, it's really a graph that consists of a number of nodes, a number of edges. The edges are directed, right? So that's the reason that we call that as a direct digraph. And it also consists of three special things, right? So S is the source, and the T is the sink. This sometimes usually people write this is as source and this as sink, and C is the capacitive function. Right. So you should really just imagine that this is as a mathematical way abstracting the water flow pipeline, water flow pipeline. So you really just imagine that all the edges are really just the pipes, right? That allows you to circulate water, so either liquids or maybe just oils, right? So, and for instance, if you look at if you look at the edge that's connecting S between, say, this node A, right, SA, right? So there's a number 10 here. That basically that means that the throughput of this pipe is, right, say the 10 unit of flood, 10 unit of waters, right. What do I mean by throughput? It's really just you can imagine that there's a pipeline. You can really just dump the waters inside the pipeline, right? The way we measure the throughput is, for instance, like if it's within 1 minute of time, how much water can pass through this pipe, right? So this is the throughput, right? And basically, more or less, this is really just physically, I guess this is really just proportional to the area of the surface, right? When you cut out, when you make, how can I draw? Like, let me draw a knife, right? The cut out the pipe, like you can look at the surface, and then the throughput is usually proportional to the surface, right? So, and similarly, like if you look at the edge that's connecting A to B, that basically means that there's a float. The throughput is 15, right? So also just notice that this all the edges here are directed edges. So that really just means that if there's a pipeline that's helping you to moving A to B, does not imply there's another pipeline that's helping you to moving from B to A, right? So in fact, it's really true that it's impossible to move any unit of water from B to A. Impossible to move water from B to A. Right? So now the high level question is that suppose that your salt, like just suppose you have a lot of waters that are stored at a source location, right? So this, you should really just literally view that as the source of the liquid you want to try to push through, and then you want to push all the water towards the so-called sink, and our goal is to be able to find a way to a planning to transport the water. Like for instance, you can go through the waters that's really moving towards this path, right? So what's the throughput here, right? So now we can ask the question, what's the throughput? What's the max possible throughput? Right? Right. So the max throughput basically is constrained by the bottleneck, right? So there are three numbers over here, 5, 8, and 10, right? So imagine that, right? If you have three pipeline, one is smaller, that can only dump 5 unit of flow every minute, right? The second one will be a bit larger, right? That can dump you like 8 unit of flow every minute. The last one is largest, that can dump you 10 unit of flow in the every minute, right? So now you sort of have a water that's pushing, right? I don't know how can I draw the water, right? So this is the water is pushing, is being pushed through the entire pipeline, right? So just imagine there are some connectors magically connecting all these pipelines, right? So these are the sink, right? So now how much you can push through, right? So basically when you push through the waters, right? So intuitively, right? So the bottleneck, it's really just the smallest ones, right? So you can only push through 5 unit of waters through this line, right? So this is you can push through 5 unit of waters through this one at most, right? This is how you use one single pipeline, one single pipes to push through water, right? So, but what makes the entire thing difficult is that you can actually use multiple paths to push through the waters, right? For instance, you can sort of push through 5 unit of waters through this path, right? 5 unit, 5 unit, or 5 unit, right? So, and then you can actually also use a second path, right? So this is you can use this path, right? So you can push, like, say, like 5 more units over here, 5 here, 5 here, 5 here, right? So what does that really mean physically? Physically, if I draw the same thing again as we did last time, but just now, we're really just saying that, like, look at this pipeline. This pipeline has the size of this pipeline is pretty small, I'm drawing 5, right? This capacity is 5 here, right? The size of this pipeline, as I mentioned, is a bit larger, right? So, and the size of this pipeline is the largest, right? This is what we draw just now, right? Let me just let me just use the same color to draw the draw everything, right? So I'll draw this, right? So this corresponds to all these 3 edges, right? So now we can also draw the pipelines that are using the second pass, right? So we sort of see that like this is the source, right? So for the second pass, right? If I'm drawing this one, so let me draw this one first, right? I really shouldn't use this solid ones, right? Sorry about that. Let me try to figure this out, right? Right. So this one is sort of maps to the edges, sort of maps to the pipe here, right? So what I'm doing is that really I'm just physically drawing what's going on, like for the to allow us to push the flow as we mentioned here, right? So I'm sort of drawing the pipeline, right? The second pipeline, the pipeline here has 10 unit of flow, right? Can push off 10 unit flow, and this one can help us to push off 15 unit of flow, right? So in general, both of them are thicker, right? So now, when I really push through the things like what I did just now, right? Let me just draw this a bit heavier, right? So I'm just trying to push 5 unit of flow here, right? This is, you can really imagine that now the water goes through here, right? So there are 5 unit of water that's pushing towards that direction. That's the first thing. And the second thing is that now we're also sending another 5 unit of water from a second pass. Now this start to get a bit interesting. Now just imagine that 5 unit of water goes to here, right? In total, the capacity here is 10, right? This is highlighted by this number, right? This 5 unit of flow can go to here again, like this is, we only use the 5 unit of a set capacity out of the 15, right? The 15 is the number here, right? We can sort of, it's a bit not visible anymore, right? So that we do 5, right? This is 15. This comes from here, right? So now, sort of like you sort of imagine there's some sort of gateway that sort of merges the two flows together, and then there are 5 unit coming from here, 5 unit coming from here, right? So at the end, this two 5 unit of flow sort of get merged, and then now there are 10 unit of flow that need to be circulated towards the right, right? So there are another 5 unit of flow here, right? So these are the 5, these are the 5. When we add them up, it's 10 unit of floats that's going through here, right? But on the other hand, if you look at here, right, the capacity also 10 unit, right? So this sort of really just highlights one single idea, right? The flow, you can really think that as water. When the water meets, they merge, right? So then they sort of there are 5 unit water from the green one, another 5 unit from the blue one. Then when they merge, you just simply add them up, right? There are 10 unit flow that's moving towards the last segment, right? So this is how we do the planning, right? So we can sort of utilize multiple passes to really push through the flow. And our high-level goal here is really to understand how can we design an algorithm to really push through, to utilize different passes to push through as much water as possible through across this whole network from S to T, from the source to the sink. Right, so this is the high-level goal, right? And then, as I mentioned, what I did just now is really just to give you the intuition, how does this kind of so next, let's formalize this max flow problem, right? So we sort of flip the direction. So in the lecture slides, it talks about the mean cost first. Now we sort of want to flip the order. We want to talk about the max flow first, right? So this is the maximum flow, right? So we sort of want to identify, right? So a set of flows, right? So basically, if you just sort of at this moment really think this, just only imagine the flow instead of the network, right? So imagine the water, right? Imagine the water, right? Water we want to push through, right? So now we sort of want to have a function that really just describes the water. What's the water, right? So So the function basically is it's really just at the end of the day let's say that we plan to push through the water in a particular order, right? So I don't know, maybe it's not really consistent with so the graph here may not be completely consistent with the graph here, but let's say that we want to follow an arbitrary graph. At the end of the day, this is how we decide to push through things. This is 5, this is 6, this is 6, 5 and 6 needs to s to 11, 11, and this is 3, 3, 3, right? So eventually we sort of managed to push a total number of 5 plus 6 plus 3 equal to 14 units of waters from S to T, right? So now we sort of want to sort of have an idea. We sort of want to articulate what we mean by pushing through the waters, right? So pushing through the waters is specified by a function f, right? So how can we specify like this whole planning, right? So basically, it's really just that what we are essentially doing is to put a number on each edge, right? The number here basically reflects the amount of flow we plan to push through this edge, right? So I'll put a number on each edge, right? And the number reflects the amount of water we plan to push through each edge, right? So and then this number really needs to satisfy certain constraint in order to make it feasible, right? So just remember that there are two set of numbers here, right? The first set number would be the originally what's the capacity of the graph, right? So basically they really just correspond to the input of the graph, right? So it's all these numbers are the capacity of the graph, right? The second set of number would be one possible way of pushing through the water, right? So this is the capacity, and this is how we plan to push through the waters, right? So it's really just like that you have a cup and then you have certain amount of water, right? So the one number represent the capacity of the cup, the other number represent how much what's the portion of the space we are going to use, right? So this one is part of the input. One is sort of the flow we want to design, right? So basically at this moment we sort of want to articulate that what would be a legitimate flow. So we need to sort of put some constraint on f, right? So let's really just look back what we have been doing, right? So basically we sort of want to describe the way we plan to push through the water by using a function, right? This function essentially really just assign weights to each of the edges, right? And the weights basically just reflects how much water we are going to put, right? This is what's written here, and there are some weights, some assignments that makes the plan feasible or realistic, and there are some assignment that makes the plan infeasible or unrealistic. For instance, if we say that we plan to push a number 100 unit of flow through this edge, but if I look at this edge, right, so the capacity here, it's only 10, right? So if I change the color here, the capacity is only 10, but I sort of want to push through 100 units. So basically that's impossible, right? So you have a cup that only has the capacity volume to be 100 milliliter, and then now you say I want to store 10,000 1,000 milliliter out of this cup, right? Basically this is infeasible, right? So you just cannot push through more water in a unit amount of time than the capacity that's specified by the pipeline, right? So basically this is the first constraint we are seeing here, right? So it has to be smaller than the capacity unit than the pipeline, right? If the capacity is 10, then you can push through at most the 10 unit of flow, right? Also, it has to be at least a non-negative number, right? So we do not allow negative flow, right? Physically, it doesn't make sense, right? This is the first thing. And the second thing would be the conservation of the, what people said, the conservation of the flows, right? So what does that mean, right? So this is really just a very natural physical law, right? So if I look at any arbitrary node, right? So the conservation of the flow basically says that if I count all the flow that's coming into me and count all the flow that's going out of me, then that should that should be the same, right? So if I have, say if I have 5 unit plus 5 unit plus 0, right? 5 plus 5 plus 0, right? I'm looking up all these first three numbers. So if I look at all the incoming flow, it's 10 unit, then I have to push out 10 unit here, right? So it's really just in general how much that's coming in has to be consistent with how much that's going out, right? That's a very, very simple rule, right? The flow cannot appear in the middle of the transportation, and the flow cannot disappear in the middle of transportation, right? So in some of the real world settings, like it's actually allowed to formulate a problem where when you circulate the flow through a network, like your flow really just get discounted because of the frictions or some transportation losses when you when you push 10 unit of flow through a gateway, maybe at the end there only 9 unit of flow that comes out, right? There, in practice, this kind of setting will happen, right? It like it's each gateway will suck a bit of the flow, right? Because of the engineering limit or because of the tax that we are paying. But when we really allow this kind of formulation that where the flow conservation is violated, this problem becomes much more complex. So in our own setting, let's start with the most simple setting, most simple form of the problem. Then we will just simply assume that there's a flow conservation, right? So the flow conservation essentially just says that for any node, the incoming flow would be the same as the outgoing flow, right? So also notice that for we are I sort of lied a little bit. Well, I just now I said for any node, but in fact that it's really for any node that's except the S and T, right? So for S, we really just assume that it's really the source of the storage. All the flow is storing here, all the water are storing here. When we push out things, right, it's really, we do allow the water push out from the middle of nowhere, right? So we are really pushing out 25 unit of things out of S here, right? So maybe I need to erase that a little bit, right? 25 unit of things here, right? But nothing comes in, right? You really just should imagine that S somehow has infinite amount of water that you can just freely push out as much water as possible as so long as it's feasible in other places, right? Similarly, if you look at the destination, right, what's the source here, right? So it's really is at the sink, right? So you should literally just treat it as a sink in your kitchen or the sink in your restroom, that all the water arrives there and sink to nowhere, sink to or disappears, right? So maybe you really just should view that as the consumer's side of the water, right? So when all the water reaches this particular node, our job is done. That we don't need to worry about where the water is going to move to, right, afterwards, right? So that's the reason that in order to conserve, so when we talk about the flow conservation constraint, it only need to be satisfied in all other nodes except S and T, right? We can exclude S and T doesn't need to have the flow conservation property. Right? So in other words, in order to design and have a legitimate assignment, we really just need to have two constraints. The